Okay, welcome back to COSC 2325. This is chapter 3 that we're going to be starting. And before you start chapter 3, make sure that you have set up Visual Studio and that you've gone through what's on Canvas and tried that small test program that I put on there, and that everything runs okay, because we're going to be using it for this chapter. So in this video, we're going to cover the basic elements of assembly language, adding and subtracting integers, and assembling, linking, and running programs. And then in the second part, we'll cover these 3 topics. So the syntax for assembly language is that we have 1 statement per line. We cannot have any more than 1 statement per line. Each statement is either an instruction, which the assembler is going to translate into machine code, or an assembler directive, which tells the assembler to perform a specific task, like allocating memory for a variable or creating a procedure. And we'll look at these in the next slides. So here is an instruction, what an instruction would look like. So the instruction is executed at runtime by the central processing unit. All instructions have a label that is optional. So you can have a label. You don't have to have a label. So if it has these square brackets, it means it's optional. We have a name or a mnemonics that's required. Operand or operands are optional, and then a comment that is also optional. So here in this example, start is a label. MOV is a mnemonics, and it means that we're going to be moving something into a register. So the operands for this move statement is CX and 5, and the 5 will be moved to the register CX. And then comments start with a semicolon, and then you put whatever you want after that semicolon. But remember, they can only take up 1 line. So here's an example of an assembler directive. You have main, procedure. So procedure would, PROC would be the directive. Okay, labels and name fields. So name fields are used for instruction labels, or what we call code labels. And we're talking about name fields or labels. It would be this right here, this part. So we have instruction labels or code label, procedure names, or variable names or data labels. The assembler translates these names into memory addresses, and they have to follow the identifier rules. So just like in our higher level languages, we had rules for identifiers like variables, names of procedures, or names of functions, or names of methods, constants. In assembly, we also have that. So let's look at those, some of those rules. So reserved words cannot be used as identifiers. That's just like any other language. Instruction mnemonics, such as MOV, add, move, add, or multiply, are reserved words. Register names like EAX and BX cannot be used as identifiers. Directives like invoke, and end procedure cannot be used as identifiers. There's certain attributes which give you the size and usage information for variables and operands, like the size of a variable word that you looked at in, I believe it was chapter 2. or byte. So those are going to be also reserved words and cannot be used as identifiers. Operators used in constant expressions cannot be used as identifiers. Predefined symbols that return constant integer values at assembly time cannot be used as identifiers either. They're at the very end of your book, there's an appendix with a reference that has all of the reserved words. You don't have to look at it. You'll just start getting used to what is reserved and then just not use it as a identifier. And remember, these identify variables, they identify procedures, labels, things of that nature. Identifiers can be between 1 and 247 characters. We never make really large identifiers. We try to keep them small, but we do try to keep them to be something that makes sense. So if you're creating an identifier or a variable to hold the sum of two numbers, then we wouldn't call that variable x, although we could, but we want it to be descriptive. So it can be 1 to 247 characters, including digits. It is not case sensitive. And just like C++ and Java, those are not case sensitive either. Well, actually, they're case sensitive. I take that back. So C++ and Java, if I call an identifier lowercase sum, then from then on, I have to call it lowercase sum. So in assembly, I don't have to do that. So that's what it means by not case sensitive. And then the first character has to either be a letter, an underscore, an at sign, a question mark, or a $sign. We're going to keep our identifiers for convention purposes. We're going to keep them short but descriptive. So if it's like going to hold a tax rate, we'll call it tax rate. We're going to start them all with letters. So our identifiers are going to start with letters. We're not going to start them with underscore, at signs, question marks, or $signs. Mnemonics and operands. So instruction mnemonics are memory aids. So they just help us. They're just a few letters to help us remember what that instruction means. So MOV is just 3 letters that help you remember that it means to move something into a register. Add, subtract, multiply, increment, and decrement. So that's what the word mnemonics means. Operands, we have things like constants. So just a plain number, 8, a 9, a 100, 1,000, that's a constant. If you've taken C++ or Java, you know they're called constant literal. So it literally just means an 8. Then we have constant expressions. So it's constant, it never changes when the program runs. 8 plus 9 will just stay there, it will always be 8 plus 9. So it's not a variable. And then an operand can also be a register, and an operand can be a data label, like sum. Sum would be a variable, or what we call in assembly a data label. Constants and constant expressions, so this right here and this right here, you'll hear them being called immediate values. And what that means is that the CPU doesn't have to go and get that value and read it from memory. It is there, it's immediate to that instruction. Instruction format examples. So here we have a label that does not have any operands. So we can see that, we can do that. Here we have a label that has 1 operand. I'm sorry, I keep calling it label. So if we go back to here, it's going to be either a mnemonic like this, or a directive. So here, this is going to be a mnemonic or a name. And it has one operand. And here we have, we also have an operand. Here is, this operand is a register, and this operand is memory. So it's going to be what you would refer to as a variable. So my byte would be a variable. These are mnemonics that have two operands. So in this add expression, we're taking this register and putting it here. So we can have two registers. We can have a data label or a variable, and then some constant. We could have a constant expression over here that gets added to this EAX. So here we're incrementing what's in this register. Here we're incrementing what's in this variable. Here we're adding these two registers, the values inside the registers. Here we're taking this constant and we're subtracting it from whatever's in this variable. Here we're multiplying two constants, and then we're adding that value to whatever values in EAX. We call the first operand the destination, and we call this the source destination. So I'm typically reading it this way as you see me, because this is what gets subtracted from that one. This is what gets added to that one. This is what gets added to that one. Comments are good. Okay, so again, comments are things that start with a semicolon. We want the comments to really be specific, and you want to be able to tell the user what's going on at each line. We're also going to start our programs with a comment that has your name, which is you're the author. So the author, the date that you authored that program, and a description of what the program does. Typically, when a program is revised by somebody else, or even by you. So let's say you wrote the program, a year later you have to revise it, or somebody else revise it. Then after that, they put who revised it and the date and what revision they made. You can also have multi-line comments, and it would look something like this. It's going to begin with the word comment, and comment is a directive. And then you're going to choose any character you want to choose, just that it's not a character that you're using in your comment. And so you'll have comment, some symbol or character, and then end it with that same symbol or character that you chose. So right here, I could have chosen an exclamation point, a pound sign. If you want to use pound signs, you can do that. So everything in here in the middle is the comment. Okay, data. In assembly language, you can express data as binary. And if we have a number that is binary like this one, 1101, the way that we can tell the way that we can be able to tell whether this is a decimal or binary is by putting a B. So if we don't put a B at the end, then the program thinks that it's decimal. By default, it's going to be decimal. We don't put a B there. Decimal can have a D. Again, these are capital or lowercase. It can have a D, and it's optional. So if I don't put like 42, if I don't put anything after, then automatically it is defaulted to a decimal. Hexadecimals have to begin with a digit. They cannot begin with a letter. If they do begin with a letter, for example, like, don't have an, oh, here's the one. So let's say that it's A5H is the hexadecimal number, then you just add a 0 in front of it. Sorry, if the hex is A5, you add a 0 in front of it and then an H at the end to say that it's hexadecimal. And then characters and character strings is a data type that we can also use. And those are going to be enclosed in single or double quotes. Unlike Java and C++ and other languages, like C programming, etc., characters can either be in double quotes or they can be in single quotes. Same thing with strings, they can be in double quotes or they can be in single quotes. So let's take a look at these examples. So 1 in the show, 1 1 1 0, because it doesn't have a B at the end. And if you want, you can pause the video and see if you can figure out what these are. So it doesn't have a B at the end, so this is going to be decimal. This is going to be binary. This is going to be decimal. This is going to be a signed decimal. Remember here, this is optional. We don't have to put the D. Now, the reason that we would put the D there is just to let the user know, yes, this is definitely a decimal, but it's not necessary. This right here has a comma, so this would be invalid. Value. This one is 3F40. So this is a good hexadecimal number. 1B56. So this is a hexadecimal number because it has a B in it, but it doesn't have the H. So this would be invalid. This one starts with an F. It's a hexadecimal number, but it can't start with just an F. It has to start with a 0. This would be invalid. This is the same thing as this one. We now added the 0, so that makes it valid. Okay, so let's look at integer expressions. This is going to be the same thing that you've had in other programming languages. It's an order, it's our operators in the order of precedence. So the order of operation, as you say in math. And so the order of operation is that anytime we have parentheses, that's going to be operated first. That's going to be first level of precedence. This plus and minus is a plus and minus that you put in front of a number like -5, -6. Doesn't mean subtraction. So it's a unary plus or minus, meaning that you're going to have a negative or a positive in front of one number. So that gets executed second. That's second priority. Then third, precedence is multiplication division. And remember, it's whatever comes first and it reads it from left to right. So if division comes first, we're gonna do that first. Then we have modulus. Remember that modulus gives you the remainder of two numbers that you divide. So if you have 6 modulus 3, 3 goes into 6 2 times evenly with a remainder of 0. But if you say 6 divided by 5, 5 goes into 6 1 time evenly with a remainder of 1. 5 divided by 2, the remainder is 1, because 2 times 2 is 4, remainder 1. Okay. And then lastly is addition and subtraction. So here's some examples down here. So 16 divided by 5 is just going to give you a whole number, because you're saying, I have an integer, I'm dividing it by an integer, I'm going to get back an integer. This is the same thing as our high-level languages in C++ and Java that you've taken before. So 3 times 5 is 15. Let's look at modulus. So modulus here, how many times does 3 go into 25 evenly? That would be 8 times. 8 times 3 is 24. And then there's a remainder of 1. Okay, looking at this one, the first thing that's going to happen is parentheses. So we'll do 3 plus 4. 4, 5, 6, 7. So this here is a -7 on this side. And then on this side, we have 6 minus 1, which is 5. And so now we have, let's see if I can, maybe, no, it's fine. So I have -7 times 5 will be -35. Here, we don't have parentheses. So the first thing that's going to happen, I'm trying to see if I can write on here. Draw. Let's see. Okay, so here the first thing that's going to happen is we're going to multiply. So that's priority 1. So 6 times 4 is 24. 6, 12, 24. And then the next thing we're going to do is we're going to start from left to right because we're going to add and we're going to subtract, okay? So we're going to do -3 plus 24. This is 24 right here. Oh, it just makes me draw. So -3 plus 24 is 21. And then 21 minus 1 is 20. So first we do multiplication because that has a higher priority than addition and subtraction. And then because we have both, we're just going to go from left to right. And let's see if we can erase this. Okay. So the next thing we're going to look at is adding and subtracting integers and how we do this in code. So we're going to look at the code. So here's an example of a program that adds 2 integers together. So here's where the code is right here. Here's where we do the addition. So we're going to take this program from the top and just talk about each one of these and go over what they mean. So first of all, this one's easy, right? This is just a comment. And again, typically our programs are going to start with author, date, and description. And that's going to be required for your submissions. Okay, so let's start at the 386 directive. So these are called assembler directives. So 386 identifies this program as a 32-bit program that can access 32-bit registers and addresses. That's this line right here. So it's not going to allow us to access anything greater than 32-bit registers. All right, the next line, the next directive is model flat, comma, std call. So flat, comma, std call, this right here is going to be some values that are passed to model. So model is a directive also, and it uses the flat model, which is a memory model. It's a memory model, the protected mode memory model. So it's a linear design with no combined segment offset addressing. And then std call parameter tells the assembler how to manage the runtime stack when procedures are called. So a procedure is like a function in C++ or a method in Java. You know, procedures have names and you can pass them parameters, you don't have to, and they can return values and they don't have to. So this right here tells you how to call these procedures, and we're going to go into this a little bit more in a different chapter. But let's take a look at, let's just go back and review runtime stack in the next slide. So if you remember, the runtime stack is going to be a group of memory locations. This is a stack right here. And we draw the stack going up, but really the stack is just memory locations that are right next to each other. And these are in read-write memory. So the stack is in read-write memory of any microcomputer, and it's used to store the contents of our registers. So if we say like EAX, 5, we put 5 into EAX, we would store the contents in the stack. We would also store the operands and memory addresses in the stack. So this is just a before and after of the stack, but this STD call talks about how we manage that stack, and we're not going to get into that right now, but that's what it does. So the stack directive, so going back over here, we have a stack directive. And the stack is assembled as a uninitialized segment of a finite size. So we have to tell it what size stack we want. And this is the size. So it tells it that the assembler to reserve this many bytes of uninitialized storage. So we have that many bytes of storage. The operating system initializes, if you remember me talking about the stack pointer, the stack pointer is going to be the address of the very first byte above those 4,096 bytes in the stack. So that's going to be the stack pointer, and it tells us where the stack begins. Where to find that stack? Okay, function prototypes. So going back to our program, we've looked at this, this, and this. Then we have exit process prototype. And then we have this name that we made up. We made up the DW exit code. And then we passed it a parameter, which is the size of, I'm sorry, we made a data label of this size of double word. So there's a data label called DW exit code that is this size. So anytime, so we'll go back over here. So anytime that we create a function prototype, we have a function name. So this is the name. So we make up this name, exit process. We have a keyword, proto. So this is a keyword. And then we have our input parameters. And here's the function call. We say invoke, name of the function, and then, so invoke exit process, and the parameter is going to be a number. And what happens with this is when we finish the program, just like in C++ and Java, we have a main, and in C++, you define your main int void main. So, and then you return 0, and it returns 0 to the operating system. Well, this is the same thing here. Here, when we say invoke exit process, that 0 goes to the operating system saying, hey, this process, everything ended okay. There weren't any problems. So here's the end of main. Things went great, wonderful. And then we would pass it a different number if there are problems. And there has to be something reading what these programs return. And then it could be a text file. It could be like a manager sees a text file and says, oh, okay, all my programs are returning 0. That's good. Or this program had a problem, and it's problem number 2, and 2 means something. So this invoke goes with this line right here. Okay, so what we're going to do is we're going to run this program, and what I've done is I uploaded this program as an ASM file. It's under it's with this presentation so that you can actually pull up that program through Visual Studio if you want, or if you want to just type everything in, you can type everything in, okay? So I'm going to go ahead and open Visual Studio and run the program, but I'm going to have to stop this video and do another video because it's on my other machine. I'm running on my Mac side right now, so I didn't think about that when I started the video. So I'm going to pause it or stop it, and then I'll start the next video with the next section.